Hello, welcome to Curated. Let's start with today's problem, which is asked in interviews at companies like LinkedIn. Okay, the question says you are given an N-ary tree. So, N-ary tree means each node can have any number of children. It's not like a binary tree, which can have maximum of two nodes. So, your task is to remove all the leaf nodes, that is, the nodes with no children, and note them down. Then repeat the process on the remaining tree until the tree becomes empty. At the end, return the nodes removed at each step as a list of lists. So let me explain. So for this problem, what would be the output? So first, note down all the leaf nodes E, J, G, C, H and K and remove them. Now in the remaining tree, note down the leaf nodes, that is F and I, and remove them. And in the remaining tree, the leaf nodes are B and D. Add them to a result list and remove them. And in the remaining tree, the leaf node is nothing but A. Add it to the result list and remove it. So this would be your output. That is a list of leaf nodes removed at each step. I have drawn the tree again. Think about what is a straightforward approach to solve this problem. The straightforward approach is start from the leaf node, traverse over the whole tree and find all its leaf nodes and add it to the results list and remove the nodes from the tree. Once again start from the root node, traverse through the remaining tree, find the remaining set of leaf nodes, add them to the results list and remove them from the tree. Keep repeating this process till the root node becomes null. Right? But what is the problem with this approach? The problem with this brute force approach is you are actually simulating the removal of nodes layer by layer, which is a messy process, right? And you are also traversing the whole tree again and again, starting from the root node. So in the worst case, the time complexity would be big O of n square for a skewed tree, right? Instead of removing nodes, think when would a node become a leaf? Leaves are already leaves, so their leaf at round 0. Their parents become leaf at round 1. Their parents become leaf at round 2. Wait, that's just height, right? Like the height of this node is 0, the height of this node is 0, the height of this node is 0, the height of this node is 1, here the height is 2, here the height is 0, the height of this node is 0, the height of this node is 1, the height of this node is 1, the height of this node is 2, and the height of this node is 3. So height is nothing but the removal round of that node. So in the results list, the first set of leaf nodes that would be removed would be the ones with height 0. That is E, J, G, C and K, right? And the next set of leaf nodes that would be removed would be the ones with height 1. That is F and I. And the next ones would be the ones with height 2. So B and D. And the next would be the ones with the height 3. That is A. By finding the heights, we get to know at what round each node would be removed. We already know the heights intuitively. Now let's see how post-order DFS traversal will help us in finding the heights and solve this problem. We'll also calculate the results list along the way, which will be the output at the end. So let's start DFS traversal from the root node, that is from node A. When we are at A, we cannot decide anything yet because its answer depends on its children. DFS will go as deep as possible. So from A, we go to its first child B. From there we go to B's first child E. E is a leaf node, right? So height would be 0. We add E to the first list. We go back to its parent B. From B we go to its next child F. It's not a leaf node. Go to H. H is a leaf node. Height will be 0. Add it to the first list. Then go back to F. Height of F would be the maximum of all its children's height plus 1. That is 0 plus 1. It would be 1. So add F to the second list. And then go back to B. From B go to the next child G. G is a leaf node. Height would be 0. Add it to the first list. Then go back to B. Height of B would be the maximum of all its children's height. That is 0, 1, 0 plus 1. So height of B would be 2. Add it to the third list. From B, go back to its parent A. From A, go to the next child C. C is a leaf node, so height would be 0. Add C to the first list. Go back to A. From A, go to its next child D. From D, go to its next child H. H is a leaf node, height would be 0. Add H to the first list. From H, go back to its parent D. From D, go to the next child I. From I, go to K. K is a leaf node, height would be 0. Add K to the first list. Go back to I. Height of I would be 1. Add it to the second list. Go back to H. Go back to D. Height of D would be the maximum of height of H and height of I, that is maximum of 0, 1 plus 1. So height of D would be 2. So add D to the second list. From D, go back to A. So height of A would be maximum of the height of B, C and D. That is maximum of 2, 0, 2 plus 1, that is 3. So height of A would be 3. So add A to the fourth list. So this would be our output. So the time complexity would be big O of n, because we visit each node exactly once, correct? The space complexity would be big O of h, where h is the height of the tree which is taken by the recursion stack space. I mentioned the space complexity excluding the output result. Okay. Let's start coding the solution. I will be coding in Java. The logic is obviously the same in any language, so you can follow along. This is the definition of each node in the tree. It has value of type character and children list of nodes. And this is the method find leaves which you are supposed to solve. It takes the root of the tree as the input and returns list of leaf nodes removed at each step. Okay, so let me start coding the solution by declaring a variable result that you return at the end, and I'll initialize it to an array list. As discussed, we will be using post order DFS traversal to solve this problem. So I will be declaring a method DFS which takes the root of the tree as the input and the result as a second input which we are supposed to update. The DFS returns the height of that particular node at each iteration. So it will be returning int. Okay. Now if the root equal to null, we return -1. Because if the node is missing, we assume that its height is -1. So that when we add 1 to it, the height of the leaf node will naturally become 0, right? And now let's move on to calculating the maximum height among all the children's height. Let me declare the variable as max height and initialize it to -1 and iterate over all the children of this node root. So node child, get the list of all its children, that is root.children. For each node, find the height, that is child height is equal to DFS of pass the child as the node and the result variable to the DFS function. So update the max height variable with math.max of max height comma child height. So this will update the max height variable with the maximum child height, right? Now the height of the current node would be the maximum height of all its children's height plus 1, right? And now we will get the list of this height or level and then add the node's value to it. Before that, check if a list already exists at that height or not. If it's for the first time, then it will not exist and you need to add an empty list. Okay, so we added the root value to the list at this height, and at the end we return the height of the node root, which is height. Okay, so this will iterate over all the nodes of the tree recursively and find their heights and add the root value to the list corresponding to their height. Okay, so let's call the DFS function and pass the root of the tree and the result variable. Okay, so this will update the result variable and at the end we return the result. Okay, now let me try to run the solution on this input, which is the same as the input that I used in the dry run example. Okay, let me try to run the solution. Okay, we got the expected output. Hope you understood my explanation. Thank you.